the third objective, what is the first word? Electric field. So what is electric field? So let us consider a positive charge. Let us consider a positive charge. The space around the charge, where its influence is felt. Okay. So influence. So what is the meaning of influence? Here it may be attractive force or a repulsive force. So when I am bringing another positive charge, then it experiences a repulsive force. When I am bringing a negative charge, then it experiences a attractive force. So attractive force or repulsive force is the influence. The space around the charge where its influence is felt is known as electric field, or otherwise the electric field is defined as force experienced by unit positive charge. Force experienced by unit positive charge. Okay. Electric field due to point charge. Electric field due to point charge. Okay. So for that, let us consider a charge Q. Around that, it has some space. In that, it experiences a repulsive force when I am bringing the test charge. Okay. So positive, then it experiences a repulsive force. Then that force is given by 1 by 4 pi epsilon 0, product of two charges. So we can take Q naught divided by, what is the distance between them? That can be taken as R square. So F equal to 1 by 4 pi epsilon 0 Q naught by R square. Now substitute the value in this equation, then automatically Q and Q getting cancelled. Then electric field E equal to 1 by 4 pi epsilon 0 Q by R square. Q by R square. So how we can say electric field is directly proportional to charge because it is in the numerator. Then the electric field is inversely proportional to square of the distance between them. Okay. Now what happened to this test charge? The test charge not gets into the formula, so that we can say electric field is independent of test charge. Okay. So how we can write it in vector form? Okay. So E vector equal to F vector by Q. Or otherwise, how we can write this one? That is E vector equal to 1 by 4 pi epsilon 0 Q by R squared into R cap. So it's a vector form. So point charge, then it is directly proportional. Electric field is directly proportional to Q. Electric field is inversely proportional to square of the distance between them. The next one, electric field due to the dipole. So I will explain about the dipole in the later question. Okay. So electric field due to the dipole, it cases two. One is axial line, another one is equatorial line. One is axial line, another one is equatorial line. In axial line, E equal to 1 by 4 pi epsilon 0 to P by R cube. Here in equatorial line, electric field equal to 1 by 4 pi epsilon 0 P by R cube. Okay. For instead of or except these two, 1 by 4 pi epsilon 0 P by R cube. 1 by 4 pi epsilon 0 P by R cube. So it can be taken as axial line, it can be taken as equatorial line. So axial line is 2 times of electric field along the equatorial line. So we can say that the electric field along the axial line is always greater than electric field along the equatorial line. Okay. Now we can go. Electric field is directly proportional to dipole moment. Electric field is directly proportional to dipole moment. So Q equal to P equal to Q into 2A. So we can include this one. So electric field is directly proportional to Q. Electric field is directly proportional to distance between the positive and the negative charges. Now, the electric field is inversely proportional to cube of the distance. Electric field is inversely proportional to cube. So, electric field for the point charge, it is inversely proportional to square of the distance. Then, electric field due to the dipole is inversely proportional to cube of the distance. Okay, do you get it now? So, we can go for once again. Electric field, the space around the charge where its influence is felt is known as electric field. The influence may be attractive force or repulsive force. Electric field is defined as force experienced by unit positive charge. In vector form, E vector equal to F vector by Q. Electric field due to point charge. So when you are bringing a test charge, it experiences a repulsive force. The force is directly proportional to product of the two charges and inversely proportional to square of the distance between them. So E equal to 1 by 4 pi epsilon 0 Q by R square. Then we can conclude the electric field is directly proportional to charge. Electric field is inversely proportional to square of the distance between them. So even though when we are bringing the test charge, then only we can say that it experiences, but it's not involved in the formula. So that we can say electric field is independent of test charge. Next one, electric field due to the dipole. So in the dipole, electric field produces in axial line and the equatorial line. Along the axial line, 1 by 4 pi epsilon 0, 2p by r cube. So electric field is directly proportional to dipole moment. Electric field is inversely proportional to cube of the distance between them. Okay. So next one, the electric field due to infinitely long, straight, charged wire. So that is the first application of Gauss law. Okay. So let us consider infinitely long, straight, positive, charged wire. Okay. So which produces the electric field? Gauss constructed the Gaussian surface. Okay. So L as the height, R as the radius. He constructed the Gaussian surface. So once again, let us consider a infinitely long, straight, charged wire. It produces the electric field. Gauss constructed the Gaussian surface, R as the radius and L as the height. Okay, so by using that we can calculate the electric field E equal to 1 by 4 pi epsilon 0 2 lambda by R. So electric field due to point charge is inversely proportional to R square. Electric field due to the dipole is inversely proportional to cube of the distance. Now we can say electric field is inversely proportional to R. Okay. So electric field due to straight charged wire is directly inversely proportional to R. Okay. Here we can go for lambda. So what is lambda? Lambda is linear charge density. So how we can say linear charge density? Linear charge density is defined as the ratio of charge to the length. The unit of charge is coulomb, unit of length is meter. So coulomb per meter is a unit of linear charge density. Now we can apply. So electric field is directly proportional to linear charge density. Electric field is directly proportional to charge. Electric field is inversely proportional to length. Then the electric field is inversely proportional to the distance. So here the third case. Okay. So next one, the electric field due to plane sheet. Okay. So let us consider a plane sheet which is uniformly charged. the gas constructed the Gaussian surface in front of the plane sheet and at the back side. Okay, so now it may be P and it may be P dash. Then the produced electric field E equal to sigma by 2 epsilon 0. E equal to sigma by 2 epsilon 0. Here, what is sigma? Sigma is surface charge density. Surface charge density. So how we can define surface charge density? Surface charge density is defined as the ratio of charge to the unit area. Okay, so unit of charge is coulomb, unit of area is meter square. So coulomb per meter square is the unit of surface charge density. Okay, so here we can say electric field is directly proportional to sigma. Yes, electric field is directly proportional to Q. Electric field inversely proportional to area. But what about the distance? There is no distance. So we can say the electric field is independent of distance. Independent of distance. So electric field due to the plane sheet is independent. Okay. So now we are going to place two sheet. Electric field due to parallel sheet. Okay. So for the first one, 1, 2, 3, 4 positively charged and the second one is negatively charged. Now we can say the electric field is 0 outside the first plate, then the electric field is 0 outside the second. So in general, the electric field outside the two plates are 0. But what about the electric field between the two plates? So E equal to sigma by epsilon 0. So between the two plate, electric field is sigma by epsilon 0. Outside the two plate, the electric field is 0. Okay. So electric field parallel sheet, then outside the electric field is 0. Now do you get it now? Do you have any doubts? Okay. Okay. Next one, the electric field due to spherical shell. Due to spherical shell. Okay. So let us consider a sphere of radius capital R and uniformly charged. It is uniformly charged. So it produces the electric field. Gas constructed a Gaussian surface. Okay. So electric field on the surface. Electric field on the surface is equal to 1 by 4 pi epsilon 0 Q by R squared. Q by R squared. Okay. The second one, the gas constructed the Gaussian surface. Gaussian surface inside the sphere of radius R dash. Now the electric field is 0. Okay. Now let us consider a sphere of radius capital R which is uniformly charged. Okay. So around that it produces the electric field. Then the gas constructed the Gaussian surface of radius R. Now, what is the electric field? Electric field is 1 by 4 pi epsilon 0 Q by R squared. Q by R squared. So once again, it produces no electric field inside the sphere and outside the sphere it produces the electric field. So for that, when we are going for a diagram or graph. Okay. So from the origin to the distance of capital R, the electric field is 0. So 0 to capital R, the electric field is 0. Okay. At R, it produces the maximum electric field, which is inversely proportional to square of the distance. Okay. So when the distance increases from the sphere to the Gaussian surface, it is inversely proportional to square of the distance. So it decreases. So this is the graph for sphere. Okay, right, okay. So from that we can go for the one more. Okay, so let us consider a positive charge. Yes, around that it produces the electric field. Yes, now I am bringing a unit positive charge. So when I am bringing the unit positive charge into the electric field, we must do some work. Then the work is here is electric potential. So amount of work done in moving a unit positive charge from infinity to one point against the electric force is defined as electric potential. So due to the positive charge, it produces the electric field. Now, what is the relation between? What is the relation between electric field and the electric potential? That is dV equal to minus E into dx. So multiplication dx comes to this as division, so that we can say dV by dx equal to minus E, or E equal to minus dV by dx. So what is dV by dx? The dV by dx is change of potential with respect to distance. Change of potential with respect to distance, then it is said to be potential gradient. Then the electric field is negative potential gradient. Okay. The unit of potential is volt, unit of distance is meter. So volt per meter is the unit of electric field. Okay. So once again I am going to the beginning. So at the beginning of this question, what we said, electric field is defined as the force experienced by unit positive charge. Okay, the unit of force is Newton, the unit of charge is Coulomb. So Newton per Coulomb, otherwise we can say volt per meter equal to Newton per Coulomb. Now do you get it now? Any doubt? Okay, fine. Right. So now we can solve the problem. Okay. So electric field intensity or electric field strength or electric field is 400 volt per meter. So electric field is 400 volt per meter at a distance of 2 meter. So the distance is 2 meter from a point charge. So this is the important word. So why we can say important word? Electric field due to the point charge is inversely proportional to square of the distance. First one. Due to the dipole, electric field is inversely proportional to cube of the distance. Due to the linear charged wire, electric field is inversely proportional to distance. Single sheet, electric field is independent of distance. Two parallel plate, electric field is 0 outside the two plate. Between the two plate, electric field is independent. Due to the spherical shell, it is dependent. Now only we see the graph. So that here the point charge is given. So okay, it will be 100 volt per meter. 100 volt per meter. Volt per meter is the unit of electric field. Upper here the word it refers electric field at a distance of, okay, so R equal to, okay, now we can go for 2. So now we are having 2 electric field and 2 distances, so that it can be named as E1 R1 and E2 R2. Okay, here we set point charge. So electric field is inversely proportional to square of the distance between them. So by using these two, we can modify the formula. E1 is directly proportional to 1 by R1 square. By using these two, we can modify the formula. E2 is inversely proportional to 1 by R2 square. Now it can be taken as equation number 1 and it can be equation number 2. Okay. Now divide equation number 1 by 2 so that E1 by E2. Okay. So to take the proportional sign, we can put equal by adding some constant. then 1 by R1 squared divided by, here also we are having the proportional sign. Once again, we can add some constant, that is 1 by R2 squared, now getting cancelled. Now R1 by R, so it becomes reciprocal. So R2 squared by R1 squared equal to E1 by E2. So now this is the required formula for us to solve the problem. So what is the value of E1? So E1 is 400 divided by E2 is 100 equal to R2 squared, that only we are going to calculate. Okay, divided by R1 squared. So R1 value is 2. So it becomes 2 squared. So 0, 0, 0, 0 getting cancelled. So 4 equal to R2 squared by 2 2s are 4. Now the division 4 comes with this as multiplication. So it becomes 4 into 4 equal to R2 squared. So to take the square, you can put the square root. So that the R2 equal to square root of 4 into 4. So what is square root of 4 into 4? 4. So R2 equal to 4. Now, the distance of 2 meter. 2 meter. So answer is given in meter. So 4 meter is our answer. Okay. Do you get it now? Do you have any doubts? So successfully we completed the third objective of the first lesson.